Let's keep moving here. The global population of skunks. This is not true. I'm just making that up. Skunks is $200,000. 200,000, not dollars. 200,000 skunks, which would be a lot of skunks all together in one place. It's decreasing by 42%. So let's find our B here. So first our rate is decreasing. It's decreasing by 42%, which means if we shift that decimal twice, that's minus 0.42. Okay, so let's find our B. B equals 1. It's decreasing minus 0.42. So let's just think of this as like 100 minus 42 hundredths, or 1, minus 0.42. So that's going to give me 60, 58. You can check by adding, so 90, and then that, yep, that equals 100. So 0.58 to the x. Okay, and let's calculate after 3 years. So put x equals 3 here. So 0.58 to the third power. Multiply that by the initial population of 200,000. 200,000, there it is. So you have approximately, part B, we'll round this because you can't have fractions of a skunk, 39,022 skunks left over. 39,022 skunks. And I really should be labeling my units here. I apologize for that. So I should be leaving dollars, 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 dollars. Okay, and the second one after 10 years. Now these skunks are going way down, way fast, so we'll see how many are left after 10 years. Multiply that by the initial population of 200,000. Only 861. Well, if you round it up, it'd be 862 skunks left over because they are dropping so rapidly every year. Okay, let's try the last two. Number 4. All right, the population of the U.S. This is fairly accurate, although I kind of rounded. 314,000. So 314 million. And it is increasing by 0.9% a year. So we'll figure out our B right here. So our rate, first off, it's increasing, so plus 0.9% increasing. Okay, so first off, let's change this to a decimal. Move it over twice. Boom, boom. That means you have 2 zeros right there. Boom, boom, boom. Right, you moved it twice. Okay, so you've got our rate. It's increasing. To find our B, start with 1. We're going to add 0.009. That's easier, so we get 1.009. Right, exponential growth. 1.009. All right, that is our function for U.S. population. Let's check 3 years from now. 1.009 to the third power. 1.009 to the third power. All right, and then we'll multiply it by 314 million. 3, 4, 5, 6. All right, looks like 322 million. That's part B, I guess I called it. So approximately 322,554,531 people. All right, second time, put x equals 10 after 10 years. So 1.009 to the 10th power times 314 million. There's 6 zeros. So we got 343,432,436 people. So it's increasing, but as you can tell, this rate is not very much. It's not 9%, 0.9%. So the growth rate is really not that much, which is why it's increasing, but not too much. And finally, Japan's population of 128,000. 128, why do I keep saying that? 128 million. Silly me. All right, it's decreasing. So population problem right there. By 0.1%. It's decreasing by 0.1%. Let's convert this to a decimal, move it over 1 and 2, so minus 0.001. So to find our B, we start again with 1. We're going to subtract 001. So let's just think you have like 1,000, you minus 1, you have 999. Right, you have 1,000 thousandths here, you have 1 thousandth that you take away, you have 999 thousandths left. Okay, you would have 999 thousandths left after you subtract the 0.001. So let's go ahead and use that. 0.999 to the x. All right, let's find it after 3 years. After 3 years, so 0.999 to the third power times 128 million. It means you only have 127 million, 616,384 people left. So you dropped, but not that much. Again, it's a very slow rate of decrease, but it is one. And after 10 years, so 0.999 to the 10th power, then multiply that by 128 million people. You're going to have 126 million. 10 years, 126,725,745 people. Okay, so we've seen how to find the rate, then apply to B, plug that into our formula, and predict the future using our exponential models.